Yeah, let me leave that. Oh. So first I will talk a little bit about the strings. So first let me remind you QFT. Normally when we say a QFT, we say QFT is a series of particles. Or particles. Okay. So the standard approach to the QFT is that you write down a field theory Lagrangian and then you quantize, etc. So this is normally called the second quantized. So the standard approach is called the second quantized approach. Second quantized approach, okay? But there also exists a first quantized approach. There also exists a first quantized approach. There also exists a first quantized approach. Is that you directly quantize, you just quantize a quantum motion say of a particle or particles. Say let's consider one particle, say a particle in space-time. Okay. So for example, if you consider a particle propagate in space-time along some trajectory, so let's parameterize this trajectory, say using a parameter by tau, which label the point along the trajectory. And then, so this will give you a mapping. Say the trajectory will map out the trajectory. Yeah, so this will map out the trajectory in space-time, which can be written as a space-time coordinate as a function of tau. Okay, so this parameterizes the word line of the particle. So this parameterizes the word line of the particle. And to quantize the particle, the simplest way is you imagine just sum over all possible paths of the particle. So essentially we are doing a path integral. So you just integrate over all possible paths of a particle, and then this is essentially the quantum motion. Just quantum mechanically you can fluctuate anyway. And then this particle, then this action for the particle essentially it's the length. So suppose the particle have mass m, it's just the length of the particle dl along the trajectory. Okay. And if you include interactions, then you have to include the trajectory which the particle can split. Say a line can split in two lines, etc. So this gives you interactions, etc. Okay. And this you need to add by hand, because the particle in principle because you can draw infinite ways of particles split into more particles, etc. So depend on your specific series, you need to specify, say, the interactions. So this you need to add by hand. Okay. So in principle, you can forget about the standard formulation of quantum field theory just to work with this particle theory. Just work with this particle theory. So the string theory is a generalization of this first quantized approach. The string theory that is currently formulated is formulated in this first quantized approach. So you just quantize motion of string in space-time. Okay. So for example, so particle case you have a point, particle string case you have a closed loop. So imagine we have a closed string. Okay, you have a closed string. A string is a one-dimensional object, so let's consider closed string. Then the string can be parameterized. So the string itself can be parameterized, say, by a parameter sigma along the string. But then this string can move in the space-time. Then it will trace out some trajectory. Trace out some trajectory. So this gives rise to a worldsheet. So in the particle case, you have a world 9. So in the string case, you have a worldsheet, which we normally call sigma. And then the sigma can be again written in terms of the space-time coordinates as a function of this tau and sigma. Okay. Now you have two coordinates to parameterize this worldsheet. So this is essentially a two-dimensional. So essentially, you have a two-dimensional surface in the space-time, embedded in space-time, and the string theory just quantize. You just consider the motion of all such kind of surfaces. Yes.
So in the case of a single particle, we have a point. Does this action actually reproduce? Like, what does it reproduce exactly? Like, is it capable of reproducing all of quantum field theory using this formalism?
Yeah, in principle, but it's not convenient. Depend on, for example, if you have a scalar particle, this can certainly easily reproduce your free scalar field theory. And if you want to reproduce phi cube theory, then you need to add this kind of splitting in your when you do your path integral, including the trajectories. You need to include this kind of trajectories, etc. Yeah, in principle, you can do it. It's not very convenient.
I see. Okay.
Yeah.
Interesting.
Yes.
How do you add interactions by hand in that?
Oh, well, you just require. You just in the path integral. You here you integrate over all such kind of paths, right? And then you have prescription. You say what kind of paths to include. And for example, if I have phi cube kind of interaction, then you say we should include this kind of paths.
But the case is it cannot be parameterized as a top, because it has the branch.
Yeah. Then you have to. Then there are technical complications in doing this.
So one other question: is string theory formulated in terms of second? Is it possible to formulate in terms of second quantization?
Not right now. So people have written down classical string field theory, and in principle you can quantize it, but that's a very complicated thing. I think nobody has successfully quantized. Even to write down the theory is very non-trivial. So the similarly to do quantization for string, you just look at you just consider the path integral. So in principle, to do the quantize the string, you can again just imagine you sum over all possible worksheet configurations, all possible this kind of two dimensions, embedding of this two-dimensional surface in space-time, that essentially give rise to all kinds of string motions. Okay, so weighted by some string action. So the simplest way to write down the string action is a straightforward generalization of this particle case. Is that you just integrate over its area. So here is just the length of the string. Here is the area. But here we also need to include. So here is the particle mass. So a generation of the particle mass is the so-called string tension. The T, which is normally written as in terms of 2 alpha prime. So you introduce a parameter, you introduce a dimensional parameter alpha prime to parameterize this T, and so this is a string tension. So this is mass per unit. String tension just mass per unit length. Okay, and this is normally called Lamborghini action. So NG, so this is Lamborghini action. We first wrote it down. Okay, so this dA is essentially just the area of the surface in the space-time. Okay, it's just straight generalization of the length of the trajectory. And yeah, depending on what kind of questions you are interested, then you try to extract those kind of physical answers from this, say, this part in the book. Okay. Any questions so far? Yes.
Do we allow paths that contract a string to a point?
Yeah. Yeah, I will show you. Yeah.
Is that two-time variable?
No, single. So sigma parameterize the string itself, and the tau is parameterize the motion of the string along the motion of the string.
But there is a time variable in sigma, or it's just a...
No, tau is the time. Tau is the internal time for the string, and then there's a time in here in the x0 in the space-time. So this can be considered as some kind of a proper time for the string, internal time for the string. Yeah, just like you parameterize the trajectory of the particle, you have some tau to parameterize the trajectory of the particle. This is the same thing.
But I mean, for any proper time, there is or itself is a 4-dimensional space-time. Why there is only like one parameter of tau, which does not have this 4 component.
No, I don't understand what you are. No, there's only a single time. You have a particle, you have only a single time, right? No, do you agree here there's only tau here? No, here I just have a line, I parameterize this line, I call it tau. Okay. Here I have a two-dimensional, here I have a string, and then each point on the string moves like a particle, and then I parameterize by a tau. It's the same thing. Yeah. Yes?
So, go ahead.
What's the metric on the worksheet? Does that make sense to us? Is it like minus plus or?
Of course, it makes sense. Of course, on the worksheet should be a Lorentzian. Whatever is the metric on the worksheet is will be induced from the space-time.
Okay, so it would be a minus plus.
Yeah, for example. Yeah, it's Lorentzian. Yeah, you can also, we can talk about, yes?
So one other question, so if that should be interpreted as proper time, if I have a string which is moving in some weird non-uniform way, how does it make sense to talk about the proper time of the string? Like you can imagine the different points on the string.
Yeah, good point. So often you cannot talk about that, and this just gives you a heuristic picture. Because the in principle string can do highly non-classical motion, and then that is encoded, say, in integrating over all such kind of surfaces. And some of them you cannot interpret it classically or semi-classically into this kind of picture. You visualize it. So I will draw some pictures later. You will see. Yeah. Yes.
I don't know, this might be a question like without a good answer, but what is the, I guess, why does the action take that form? What is that accomplishing physically? Or like, I guess maybe an easier example would be up there in the first quantization approach.
Yeah.
How does that reproduce QFT?
You say why that reproduce QFT? Yeah, how that reproduce QFT, of course, is a technical question, which you have to calculate explicitly. And but the question is, why do we choose that? The reason we choose that is it's based on various principles. So first, that thing, whatever it is, should not depend on how you choose this tau. Because you can parameterize your trajectory as any way you want. So that the L, so whatever this action should not depend on that parameterization. And also, this action should be Lorentz invariant on the space and the Lorentz boost, should be translation invariant, etc. And with those conditions, then essentially uniquely determined to be this form. Yeah, essentially uniquely determined to be this form. Yes.
So I guess if you were doing a quantization of the bosonic string, like if you were deriving the field equations, would you use Nambu-Goto or would you use Polyakov?
Yeah, that's right. If you really quantize it, you actually don't use Nambu-Goto. Nambu-Goto use it for the classical description. Yeah, I did not mention the other forms. It's just for our current discussion, it's not essential. Yeah, indeed. When you quantize it, you actually use a different form of this action. Any other questions? Good.
طبعا كل هذه التفاصيل نظرية لا تحتاج إليها. كل هذه التفاصيل، تفاصيل السترينج وتفاصيل الكيو اف تي ويانج ميل ايكويشن لا نحتاج، لأنه نظرية تتعامل مع الفضاء وكيف الفضاء يؤثر على المادة. المادة كانت كلاسيكية، كانت مادة كوانتمية، كانت سترينج، الفضاء لا يعنيه، فقط هو كيف يؤثر على المادة وكيف أن المادة تؤثر عليه. المادة عبارة عن طاقة تؤثر عليه بأي آلية وهو يؤثر عليها بأي آلية فقط. لكننا نحن كملاحظين لا يهمنا الفضاء، أو الفيزياء تطورت أنها لا تهمها الفضاء وإنما يهمها المادة. لذلك نحن نهمل الفضاء وندرس المادة. لكن إذا درسنا المادة عن طريق الفضاء سيكون أفضل بكثير جدا أن ندرس المادة عن طريق المادة. فهذا ما يجمع النسبية العامة مع ميكانيكا الكم، أن تدرس المادة عن طريق الفضاء وليس أن تدرس المادة عن طريق المادة. طيب تعالوا نواصل.
So now, for example, yeah, so say how you so depend on what kind of questions you are interested, and you try to extract them, say, from this kind of path integral. And of course, this is a highly non-trivial questions and require, say, some kind of trial and error, etc. So let me just tell you, say if I have say if I want to calculate the vacuum process, say if I want to calculate the vacuum energy. Okay, so let me call this string. So if I so remember when we talk about large N-gauge series, and if you want to calculate the vacuum energy, then you sum over all possible vacuum diagrams, etc. Okay, you sum over all possible vacuum diagrams. But suppose we want to calculate the vacuum energy in the string theory, and then you do the similar thing. You just do the what do you want to do for the string. You say you sum over all closed 2D surfaces. Okay? So the closed here is essential. So this is based on the intuition that when we, in the quantum field theory, when you sum over Feynman diagrams, and the Feynman diagrams heuristically can be considered as particle trajectories, etc. And for the vacuum process, there's no external lags. So everything coming out of the vacuum then come back to the vacuum. So that's why, so if we want to calculate the vacuum energy in the string theory, and again should correspond to the virtual string motion. And again, the virtual string motion should correspond to sum over all such kind of surfaces without any external lags. So should be closed surfaces, okay? Should be closed surfaces. So as analog of the particle case. And so as exactly as in the quantum field theory case, it's easier to do this using the Euclidean by going to the Euclidean signature, and say go to the Euclidean signature. Okay, going to Euclidean signature. So essentially, analytic instead of considering a surface in the Lorentzian space-time, you consider you analytically continue your space-time, the full space-time, to the Euclidean signature, and then this just becomes some surface in some Euclidean space, and then this is just much easier mathematical object to deal with. Okay, so that's what you get, and if you have a string, and then you have this. Okay. Okay, so now, when you sum over all surfaces, now you have a choice. First, you can sum over the topology. So we talked about before, all two-dimensional surfaces, topology is classified by this genus. And then you can sum over surfaces with a given, so you can separate the sum into sum over topology, and then some surfaces of each of a given topology, given H. Okay, so this H is the genus. So essentially, we are just summing over all possible two-dimensional closed surfaces. Okay, is this point clear? This is absolutely key point. And with this minus SNG. Okay. So now there's a very important mathematical trick, and this mathematical trick will can be justified vigorously, but I will not just put it here. I will just add it here. It said now, just in physics, whenever you see a discrete sum like this, what do you do? Or in mathematics, whenever you see a discrete sum like this, what do you do? Sorry?
Parameter that suppresses large terms.
Exactly, you add a weight. So here I will add a weight here. So here I'm summing over all topology, but now I will add by hand a weight to weight different topology. So lambda is just some parameter. So lambda is just parameter I introduced by hand myself. Okay, so this is just the weight. For different topology. So chi is the Euler number. So lambda is just some number. So chi is the Euler number, 2 minus 2h. And the lambda just can be considered as some kind of chemical potential. Some kind of chemical potential, say for topology. Okay, yeah, just like in the system, say you have a conserved charge, then it's when you add particles, different particle number, it's convenient to add a chemical potential, so lambda is like that. So even though I added it by hand now, even though I added it by hand here, but in string theory, actually this is arises completely natural from the string theory. There's a rigorous way one can show how that arises, but I will not do it here. It's not important for our purpose. And I will also introduce a notation. Say GS is equal to exponential lambda. Okay. So now let's look at this. Now let's look at this summation. So here you sum over. So at h equal to 0, you sum over all surface with the topology of a sphere, and the weight is given by gs minus 2, which is exponential minus 2 lambda. Okay. Because the chi, when h equal to 0, chi equal to 2, so this is just minus 2 lambda, and so this is 1 over gs squared. Okay. And then the torus is h equal to 1. So this is just the gs to the power 0, or the 1. So if you have genus 2, so this would be h equal to 2, then it would be gs squared. Okay. So here's a remarkable fact. So here is a remarkable fact. Here's a remarkable fact. Is that sum over topology automatically includes interaction of strings. Okay. In fact, this fully specifies string interactions. Okay. So let me just elaborate on this statement. So we can see this statement from these sums here. Okay. So now let's look at the physical meaning of those diagrams. So let's first look at the sphere diagrams. So this suppose we draw a sphere. Okay.
طبعا هنا ربما يكون لاحظتم بداية التشابه والاتفاق مع نظريتي. الآن الأمر انتقل من المادة إلى الفضاء. طوبولوجي يعني الفضاء، فالأمر انتقل من المادة إلى الفضاء، وهنا يصبح مثل الكماشة أو بداية الخيط مثلا للالتقاء مع نظرية آل يوسف. السترينك الانتراكشن بين السترينجز عبارة عن توبولوجي. هذا أمر مهم جدا، يعني مهم جدا في هذا الأمر.
So what I'm describing to you is heuristic from physical perspective. From physical perspective. So if you think about the sphere embedded in the space, so this is like. So if you think from, say, imagine your time going up. Okay, imagine your time going up. So this is like you nucleate the infinitesimal string at the tip of the sphere, and then this string propagates. So that each time you have a string, and then at some future time, then go back to the vacuum. Okay, and so you just have a string come in and come out, a string come out from the vacuum and then go back, and the sphere just describes this kind of virtual process. Say you nucleate string and then disappear again. Okay. Say nucleate string nucleation and then disappear. Into vacuum. Okay? Yes? Because it's enough for my purpose now. Yeah, I'm not trying to give you the full string theory at the moment. I'm just trying to give you the bit of string theory is enough to make that point. Say Lagrangian expansion is like a string theory. Yeah, because otherwise take the whole semester to reach the point. So now, let's look at this torus diagram, because if you want to sum over all surfaces, then you have to sum over different topologies, then you have to sum over the torus. Then let's look at what torus diagram means. So let me draw the torus in a slightly different way. Okay? So the torus, again, if you try to view the time going up, then from here, again, you nucleate a single string. But now at this time, then you actually have two strings. And then here you have one string back again. Okay? Then the torus actually describes such a virtual process is that you nucleate a string from the vacuum, and then this string split into two strings, and then these two strings come back to join again into a single string, and then go to the vacuum. Okay, so this is the nucleation out of vacuum, and then here it splits. So here a single string splits into two strings, and then here they join together, join back into a single string, and then here disappear into the vacuum. Okay, so we find by including the torus diagram, you automatically include this kind of interaction that the string can split into two strings, and two strings can join into a single string. And essentially, you don't have choice. This is just determined by the topology. Okay, you don't have choice. It just once you write down this path integral, then this is fully determined. Okay, it's fully determined. And similarly, if you look at the two-loop process, so you nucleate the string, split, join, splits, and join again. So the two-loop string again can be considered as such a such interacting process. So now the key. So now if we compare the GS dependence of these diagrams, so this one, so each diagram compared to the earlier one, you increase by GS to the power square. But for each, whenever you include a genus, essentially factory include such a splitting and the joining. So that means you can actually associate with each process to be a factor of G string. Okay, so for the sphere, you have, say from here, say if you normalize string a sphere to be GS minus 2, then now if you include, so essentially this weight which we added here is to a weight for such a splitting and a joining process. So each splitting and joining essentially give you a weight of G string. Okay? Weight G string. So in some sense, we concluded that the basic string interaction vertex is just a single string can join to two string or two string or single string can split into two string, or two string can join to a single string. And the weight for each process is given by G string. Okay. So that's effectively what this mathematical trick does. So effectively what this mathematical trick does is to assign a weight for each such a splitting process. Yes?
So if you start the nucleation, so you drew it like this for the 2-loop thing.
Yeah.
But if you start the nucleation from the side rather than
Yeah.
the bottom,
Right.
then wouldn't it like split into 3 and then back into 1?
That's right. That's because of the topology, you can split in arbitrary way, and this just tells you using this basic vertex. Then for fixed parameterization, this vertex is already enough, and you can indeed it's a very good question. You can try to slice the diagonal in arbitrary way, then that may give you some arbitrary other things. Then that's fine, and then you can assign weight for some other vertices, but they will be all consistent with these fundamental vertices. So essentially this GS, which I called to be Euclidean lambda, is essentially the coupling for the string. Okay? It essentially determines the strength of the string interactions. Yeah.
Our choice of weight is not unique. For example, we could do something ugly like e to the power chi-square and then include that.
Yeah, that's a good point. Indeed, yeah. So here is the simplest choice, and it's a choice which you can. So this is the simplest choice you can put, and this is a choice which will also arise if you properly quantize string theory. And indeed, you can write down some other string theory with a different power. It might be possible. Yeah, I mean, just as a mathematical, say at the mathematical level, nothing prevents you to add some arbitrary function of chi, and this is just the simplest way to do it, and this is the way which arises out of string theory. Yeah, so this process is not arbitrary; it's something which you can derive from string theory. Just here, I will not go through the whole thing. Any other questions?
Do we have an extra minus sign in the extra?
No.
Because chi goes more negative as h increases.
Yeah.
So it becomes larger and larger.
Yeah, because I can take G to be small. Yeah. The only thing is I want to be consistent with this power. So now here is the key. So now let's look at the external strings. So here, at the beginning, I was looking at the vacuum process. There was nothing, just everything come out of the vacuum. But you can also consider, say, some process. Say you start with two strings, then you scatter them together, you get two strings back. So you can also consider such kind of string. So you started with actually two initial strings, and then through some complicated interaction, then you have some two string back. Okay? So for example, this would be such kind of process. Again, anything can happen in between. I have two initial strings, but I have two follow strings come out. Okay. So this would be some kind of surfaces. So this would correspond to you have to sum of all possible surfaces with 4 external strings. Say 2 coming from minus infinity and 2 come from t equal to plus, 2 come out at t plus infinity. Okay. And again, you need to sum over all possible topology in between. Say you sum over sphere in between. Yeah, let me just save time, draw it quickly. So you can sum over all spheres in between, some spheres, or you sum over torus. Etc. Okay. But now if you do this weight according to this rule, okay, now if you do the weight according to this rule, something changed. Because again we want to sum over all possible surfaces with the same rule as you do for the vacuum. But now there's something important changes. He said this kind of surfaces, so these are the surfaces with the boundaries. So you want to start with two initial strings and 2 follow strings. So each initial string introduces a boundary. So now you have 4 different boundaries. So you have 4 boundaries. And so when you introduce boundaries into a 2-dimensional surfaces, then the Euler number changes. So some of you already may know this from high school. 2 minus h and minus n, and n is the number of boundaries. Okay, number of boundaries, and which is the same as the number of external strings. Number of external strings. Okay. So now if you use this rule, so now for the n-string scattering, so let me call this n, an, then you will again sum over all genuses. So now this weight, when I translate into GS, become n minus 2 minus 2h, plus 2h. Okay, so now because of this n, so I have additional power of GS to the power n. Say I can write as Fn h. Okay. So if you look at the sum. So if you look at this sum, so this is GS to the power n minus 2 come from the sphere surface, spherical surfaces, which can also be considered as a tree level from the string point of view, because the string just come out and the nucleate. And then the next order is GS to the GSN. Then this is torus topology. So this may be considered some kind of one loop process. And the GS n plus 2. So this is genus 2, etc. Okay. So now let's compare with this. So this also including the vacuum. For the vacuum, just set n equal to 0. Okay, just set n equal to 0. So now we see exactly parallel with what we see in the Lagrange gauge series. In both cases, you have summing over topology. And in both cases, you have summing, you have this expansion. And so identical mathematical structure with large n expansion in particular G string now corresponding to just 1 over n, and these external strings, say if you have some just corresponding to the glue balls, what we call the glue balls, so this kind of single trace operators. And the sum over string worksheet of, say, topology of genus H is then mapped to, say, some over Feynman diagrams of genus H. Yeah, so you see, say
الآن طبعا هو يعمل مقارنة بين QFT ومخططات فايمن وبين ما توصل إليه من ناحية رياضية في السترينج. هذه المقارنة سيربطها بعدين عن طريق الجي سترينج جي اللي هو الكوبرين كونستانت، وعن طريق الان كابيتال، عن طريق الان كابيتال، وبالتالي يعني سيخبرنا انه عند ظروف قاسية مثل جي تولى إلى زيرو والان تولى إلى ما لا نهاية، فإن السترينج أو الفيزياء التي تتحكم في السترينج هي نفس الفيزياء التي تتحكم في QFT.
Exactly parallel mathematical structure between the two. So the question is whether is this an accident or this is something deep, okay? I think I'm running out of time. Yeah. Okay, maybe I will stop here. Oh, you don't want to stop?
No.
Let me say a few words. If you look at these two sums, this sum and this sum, oh, yeah, let me call this Fn so that to distinguish them, let me call this F. So that's F. So if you look at these two sums, so the question is, can you really physically identify these two? Okay? Yeah, just say, let me just say a couple of words. Say FNH, which appear in the correlation functions, essentially just sum over Feynman diagrams of genus H, and this is the just the Feynman diagrams, the expression for the Feynman diagrams. And this one, this FH, fnh. So this is sum over, this is path integral, say minus SNG of genus H surfaces. So now remember one thing we said before is that each Feynman diagram can be considered as a partition of a 2D surface. Okay? So now if you sum over all possible Feynman diagrams, so you can also think of it geometrically as sum over all possible triangulations of a surface. Triangulations of a surface. So this kind of a partition is essentially just a triangulation of the surfaces divided into different parts, and with some amplitude, with some weight. So sum over all possible triangulation of the surface. Of course, this is precisely just a discrete form of summing over all surfaces. So this is just a discrete sum of summing over all surfaces. And so this really identifies these two are essentially the same object. So when you're summing over diagrams, you are actually summing secretly, actually summing over all possible embeddings of some surfaces in space-time. And the precise nature of that surface, of course, depends on the diagram itself. So this really tells you that the Lagrange expansion is really just a string theory. Okay, it's really just a string theory. But from here, you cannot immediately tell what kind of string theory is this, because from Feynman diagram itself, so this Lambo Goto action, which I wrote earlier, corresponding to you map from some surface, embedding of some surface in some space-time. And that space-time can be some arbitrary space-time, etc. For different space-time, of course, you get a different action. So the question is, what does this correspond to? So I give you a set of, I give you a field series, and you have those Feynman diagrams. And and for each Feynman diagram, you can write down expression for them. Just whether this really corresponding to, say, some geometric action, the Feynman diagram, whether really corresponding to some geometric action describing the motion of some surface in some space-time. Yeah, so let me just stop here.
طبعا هنا عرفنا أنه الآن بعد هذه المقارنة والمقاربة بين السترينج والفايمن دياجرامز ستكون الحلقة القادمة تماما أو الجزء القادم سيكون تماما عن الفايمن دياجرامز. لماذا؟ لأنه يريد أن يعرف ما هي الN هذه والجي للفايمن دياجرامز التي شرحها في السابق، وأيضا كما ذكر يريد أن يعرف الأكشن، أي نوع من الطوبولوجي الذي يصلح فيه الأكشن ويكون مقاربا تماما للسترينج ثيوري أو للسترينج. بالنسبة لنظريتي الأكشن يعتمد على ماذا؟ يعتمد على معدلات تدفق الزمان والمكان. معدلات تدفق الزمان والمكان. وبالتالي بالنسبة لنظريتي أن الأكشن يكون واضحا وجليا في عندما يكون معدلات تدفق المكان والزمان تأخذ قيم محددة، ويختفي هذا الأكشن عندما تأخذ قيم أخرى. وبالتالي هذا معدلات تدفق الزمان والمكان خارج الفضاء أفق الحدث للثقب الأسود يمكن أن نجد له ما يساويه داخل الفضاء لأفق الحدث الثقب الأسود. لكن عندما نأخذ في الاعتبار، يجب أن نأخذ في الاعتبار حجم أو تفاعل هذا الفضاء مع المواد، يجب أن نأخذ هذا في الاعتبار، لأنه في معادلة المثير رأينا أن M هي التي تؤثر، M هي التي تؤثر على الفضاء، M التي تؤثر على الفضاء. طبعا هناك معادلة أخرى سنذهب إليها. هذه المعادلة الأخرى هي عبارة عن M small وليست M capital. طبعا مترية رأينا M capital، لكن لم يسأل هذه M capital تعني الثقب الأسود. طيب ماذا عن M small؟ ماذا عن السترينج ذات نفسه؟ ماذا عن جسيمات فايمن؟ تعتبر M small. طيب أين M small هذه؟ ما هي يعني تصرف M small في فضاء M capital؟ طيب تعالوا نشوف معادلة غريبة جدا تخبرنا بهذا. هذه معادلة الام سمول. انظر الام سمول، ام سي سكوير يساوي سي اس 4 على 4 ار تكعيب في اي اس ناقص 2 في اللوغاريتم الطبيعي لسي تربيع على سي اس 6 على 16 جي تربيع ام تربيع ناقص 10 جي ام على سي تربيع ار. أين وجدنا هذه المعادلة؟ هذه المعادلة واضحة تماما، هي معادلة الام كابيتال في مترية على يوسف، وهي مكتوبة ام كابيتال مكتوبة، يعني مترية على يوسف التي ذكرناها من قبل اللي هي دي اكس على دي اكس على سي اكس على سي تي تؤثر مباشرة تأثير مباشرة في الام سي سكوير التي هي معادلة أو طاقة الكتلة الصغيرة. وانظر على علامة ناقص. ماذا يعني علامة ناقص؟ أن التأثير للفضاء سلبي، تأثير للفضاء سلبي، وكلما تضخمت الكتلة M كلما كان هذا التأثير إيجابي، أو كلما تقاربت المادة الجسيم الساقط كلما كان هذا التأثير إيجابي. يعني الكتلة تتضخم، الكتلة تزيد من الخارج. لماذا تزيد؟ لأنه السلايسز اللي هي مدارات حول الخارجية تتقارب، كل ما تقاربت المدارات زادت الطاقة وزادت الكتلة، وهذا عمل الكتلة ام كابيتال. عمل الكتلة ام كابيتال أو الجاذبية تعمل على تقارب المدارات، وعمل الكتلة وعمل الفضاء الثانوي العادي وهو تباعد المدارات. طيب ماذا يحدث إذا عبرت أفق الحدث؟ أفق الحدث إذا عبرت أفق الحدث فإن الحد الثاني يزيد، ويزيد مع علامة السالب، وبالتالي إنه نجد أن ام سي سكوير هذه تتنافس عليه اثنان، تنافس ار تكعيب. انظر ار تكعيب في المقام، إذا نقصت ار تكعيب هذا يعني أن المادة ام سي سكوير تتضخم. وأيضا لدينا الدالة الأسية، وبالتالي نجد أن الدالة الأسية تقبع ار، لأن الدالة الأسية أكبر من ار، بالإضافة للحد الأسي. الحد فوق الدالة الأسية حد كبير جدا ويحتوي على ار ذاته اللي هو 10 جي ام على سي تربيع ار. هذه المعادلة تجدونها في كتابي على ما أظن يسمى بنظر ميثود 43 ولا 44 كذا. تعالوا نمشي نشوف هذا الكتاب. حلقة 48 Another method to explore the space self-defense determination the black hole boundary يعني يا ربي هو نعم هو نعم. انظر إلى المعادلة التي ذكرناها قبل قليل m سكوير mc سكوير هذه هي المعادلة. فنجد أن داخل الثقب الأسود، طيب بما أنه فضاء داخل الثقب الأسود يعمل على قمع ال MC سكوير، بالتالي هو ينقص القيمة M، وبالتالي عند حد معين عندما تنقص القيمة M إلى حد السترينجز فإن ذلك يكافئ فضاء معين خارج الثقب الأسود تعمل فيه معاملات فاهمة بكل أريحية. تأتي التجربة لتوضح لنا ما هو الفضاء. طبعا نقول التجربة لكنه لا تحتاج إلى تجربة، فقط عوض في معادلتي هذه فقط عوض فيها لكي تعرف أي فضاء هو كافي لعمل هذا. الموضوع بسيط جدا في نظريتي، ليس بهذا العمق، لكن في السترينج ثيوري صعبة. في السترينج ثيوري هي صعبة جدا، لكن في نظريتي بسيطة جدا جدا، وتخبرنا أين ذلك الفضاء سواء كان داخل الثقب الأسود أو خارج الثقب الأسود كيف يتكافئان مع بعض البعض.
Would map to a leading order in the string scattering, and the leading order in the string scattering they only consider say two-level string scatterings, and then would corresponding to classical strings. And then also the single trace operator here can be mapped to the string state. Yeah, can be mapped to the string state. Okay. But this is a very nice picture, but for many years this was just a dream. It's because this guy looks very different from this guy. But this is difficult. So this signification is difficult. For the following reasons, so first, so this G just say your Feynman diagram, so amplitude for particular Feynman diagram. So G is typically expressed as product of field theory propagators. So imagine how you evaluate the Feynman diagram. The Feynman diagram essentially is just a product of the propagates, and then you integrate it with their vertices integrated over space-time. Okay, so just take the Yamil theory, and if you look at the expression for those diagrams, of course you look nothing. So they look nothing like. So let me make a few comments about this thing, because if you want to match, say if I give you a Yamil series, if I give you a QCD, then you can write down then you can go to large A and you can write down expressions for the Feynman diagrams. But if you say I want to write it as a string theory, then first you have to say what string theory you want to compare with. Okay, so first you have to ask yourself what string action do you want to compare. So the string action. So this string action, as we discussed last time, this describes the embedding of the worksheet into some space-time. Okay, so this is worksheet. Into a space-time. Space-time. So this is always this is also sometimes called the target space. So this is a space-time this string moves, and mathematically this is just this is encoded in this mapping x mu sigma tau. Okay, x mu is the coordinate for m, and then sigma tau is the coordinate you parameterize your worksheet. So in order to write down a string, in order to write down an action, of course, you have to a choice of space manifold. You have to choose your space-time, and also you have to when you fix the space-time, you have to then have a choice. Then sometimes the way to write down this string such kind of embedding is not unique. The action for such embedding is unique, so you also need to choose what the action you include. And also often, in addition to this this embedding, sometimes you can have additional internal degree of freedom. Living on the worksheet. For example, you can have some fermions. Say if you have a superstring, then you can have some additional fermions living on the worksheet in addition to this embedding. So in other words, the choice of this guy in some sense is infinite, and you without any clue, so you need some clue to know what to compare the gauge theory to. And otherwise, even if this works, you're searching some needle in the big ocean. And there's another very important reason why this is difficult. Is that this string theory is formulated in the continuum. It's formulated in the continuum. And these Feynman diagrams even if they correspond to some kind of string theory, they correspond to a discrete version of that. Corresponding to discrete, so at the best, it's a discrete version. So we expect the geometric, such a geometric picture for G, for these Feynman diagrams, to emerge only at strong coupling. Okay. emerge only as strong coupling for the following reason. So if you look at the Feynman diagram, so the simplest Feynman diagram, say we draw before, say for example, just this diagram, okay? And if you draw it on the sphere, it separated the sphere into 3 parts, okay? So discretize the sphere into 3 parts, and essentially just the sphere just becomes 3 points because each part corresponds to, when you triangulate, then each part you approximate about 1 point. So essentially you, in this diagram, you approximate the whole sphere essentially by 3 points, okay? And of course it's hard to see geometric picture from here. And geometric picture you expect to emerge when your Feynman diagram become very complicated. For example, if you have this kind of diagram, because of the 4-point vertex, in principle you can have all these diagrams. And then this corresponding to discretize, suppose this is on the torus. Let's do it on the torus. Suppose if you have for example, this could be a Feynman diagram on the torus, okay, for the vacuum energy. And now this is next some kind of proper discretization, and this will go to a continuum limit. Say when the number of this box go to infinity. When the number of boxes go to infinity, then you need the number of propagators, and the number of vertices go to infinity. Okay, so in order for continuum a picture to emerge, so you want those complicated diagrams with large number of vertices or large number of propagators to dominate. And for those things to dominate, then you need strong coupling. Because at weak coupling, this is the leading order diagram. And there's no geometry from here. Okay? So in order to have the geometry, you want the diagram very, very complicated so that they really corresponding to a fine triangulation of a surface. A weak coupled diagram with small number of lines will correspond to a too crude, will correspond to a very close triangulation of the surface. So we expect this only appears as strong coupling. Okay? Yeah.
But the case is like we have to sum over all the Feynman diagrams.
Yeah, sum over the Feynman diagram. Including those simple ones. So that's why you want to. So if you're in a weak coupling, then the simple ones. So in this diagram. So when you sum all those diagrams, each diagram you can associate with a coupling power. So at the weak coupling, then the lowest order term will just dominate. And the lowest order term have very simple diagrams. And then that's corresponding to a very crude triangulation of the surface. But if you have a strong coupling, then in particular, if you have infinite coupling, the diagrams with, say, infinite number of vertices will dominate. And then that's corresponding to a very fine triangulation of the surface, and then that can go to the continuum limit.
But the interaction and coupling constant has been dragged out from.
No, that's just n dragged out.
Oh, I see.
No, this what we call this 'to Hooft coupling still remaining.
Okay.
Yeah. By coupling, it's only n. No, this is the 'to Hooft coupling. Strong coupling we mean the 'to Hooft coupling. So example we talk about corresponding to this lambda. Yeah, and let me make more precise. So in the toy example we talked about before, so previously we talked about this example, n divided by lambda trace, say 1/2 partial phi square plus 1/4 phi to the power 4, and strong coupling means the lambda large. Okay, because the n have already factored out, so your coupling is just lambda.
Oh, I see.
Yes.
So in this part of the visualization, so the propagator integration will become the space-time integration. But I just wonder how the propagators integrate to match to the space-time integration.
Yeah. So So the propagator, propagator you do in the standard way. You just write down your propagator, and then you try to repackage that. The question you said whatever your rule, Feynman rule is, you just do that Feynman rule, and you write down this expression is something very complicated, and then you say, can I find some geometric interpretation of that? Yeah, what I'm saying is that doing from this perspective is very hard, because you don't know what thing to compare, and this is first, and second, you expect the geometric picture emerge only in those very complicated diagrams, and those complicated diagrams we don't know how to deal with, and those because they only emerge in the strong coupling limit, but in the strong coupling limit we don't know how to deal with that, and so that's why it's also difficult. But nevertheless, for some very simple series, say if you don't consider the Yang-Mills series, you don't consider gauge series, but suppose if you consider some matrix integrals, say for very simple systems, like a matrix integral, so this structure, emphasize that this structure only have to do with you have a matrices, okay? And you can have matrix valued fields, or this structure will emerge you only have a matrix integral. So there's no field at all, just have a matrix integral. That same structure will also emerge. Yeah, for example, I can consider a series, say, have a series like this. Something like this. I can have a series like this, okay? And M just some Hermitian matrices. So this is just integral. And the same structure will emerge also in this series when you do Lagrange expansion. So that structure have nothing to do. You can do it for So, but this is something. So matrix integral is much simpler, say, than a field series, because you have much less degree freedom. So for simple systems like say a matrix integral or a matrix quantum mechanics, actually you can actually guess the corresponding string series. Can guess the corresponding string series. Because also the string theory in that case is also very simple. You can guess very simple string theory.
طبعا هنا في نظرة لماذا يعني الماتريسيس تقدم حلولا أفضل، لأنه نحن نعتمد على نظرية القياس measurement theory، ونظرية القياس تستدعي أننا خارج الكتلة. يعني نحن عندما نقيس مثلا نتحدث عن الجيج ثيوري ونقيس ماذا يوجد في التفاعلات الدقيقة، فإننا أو نقيس ماذا يوجد داخل الثقب الأسود مثلا إذا استطعنا ذلك، فنحن خارج الكتلة، وبالتالي ينطبق ماذا؟ ينطبق علينا أن الفضاء خارج الكتلة هو فضاء رباعي الأبعاد، لأن الكتلة ما تفعله في الفضاء ثنائي الأبعاد هي أن تخرج بعدان آخران، أن تخرج بعدين آخرين ويصبح بالفضاء رباعي الأبعاد. طيب الماتريسيس لديها ميزة جميلة جدا، أنها يمكن أن تدخل عدد كبير من المتغيرات في معادلات قليلة بسيطة، وبالتالي يمكن أن تفترض مجرد افتراض أن تفترض أن الكتلة تستطيع إخراج أكثر من بعدين، ومثلا نقول أنه تخرج أبعاد بقدر الماتريس التي تدخلها، بالتالي أنت تحتاج لمتغيرات أكبر في معادلات أقل. لكن هي تخرج بعدين، يعني هي 4 أبعاد، لكن أنت يمكنك أن تدخل متغيرات أكثر. وهذا يعني يتفق مع ماذا أن الكتلة تعمل على تحويل الفضاء ثنائي الأبعاد إلى فضاء أكبر أبعاد وأكبر. طبعا في نظرية تقول فقط 4 أبعاد كلها، لكن أنت يمكنك باستخدام الماتريسز يمكن تفترض أبعاد إضافية كما رأينا أو سنرى هنا في هذه السلسلة أن هناك 11 بعد، وبالتالي الماتريسز أفضل في وصف هذه 11 بعد، لكن هي في الحقيقة ليست هناك 11 بعد، هناك بعدان و4 أبعاد فقط. 4 أبعاد بسبب الكتلة للملاحظ الخارجي، وبعدان بالنسبة لعدم وجود الكتلة للملاحظ الداخلي، أو داخلي يعني داخل الفضاء ثنائي الأبعاد، أو وجود الكتلة للملاحظ داخل الكتلة. وأقصد بداخل الكتلة هو فقط الثقب الأسود، لأنه إذا كنت داخل البروتون أو على سطح البروتون فإنك لن ترى لن ترى سيطرة الفضاء ثنائي الأبعاد، إنما سترى فضاء رباعي الأبعاد إلا أن تدخل عميقا داخل البروتون حتى تصل 10 سناقص 19 أو 10 سناقص 20 من المتر. هنا ستتحول الفضاء رباعي الأبعاد إلى فضاء ثنائي الأبعاد مثل فضاء الثقب الأسود حسب معادلة المترية لعلي يوسف.
But it's not possible for field theory. It's not possible for field theory. Yes.
So what do you mean by matrix quantum mechanics?
So this is a matrix integral, and I can make it a little bit more complicated. So I make this m to depend on t, and then this become a matrix quantum mechanics. Say trace m dot square plus m square, say plus m4. Then this become a matrix quantum mechanics because we only have time. And then I can make it more complicated. I can make m dxt tx. Then this becomes 1 plus 1 dimensional field theory.
So in what context does matrix quantum mechanics count?
I mean, this has some point model.
Oh.
Yeah, I'm just saying. I'm just saying this is a very difficult question. You say I don't know how to deal with field theories. Then let's start with a simple system, and then just try to use this philosophy and see whether I can do it for a simple system. And then you can show that this philosophy actually works if you do a matrix integral or matrix quantum mechanics. Yeah, simple enough matrix integral and matrix quantum mechanics. Okay. And if you want references, I can give you references regarding this. There's a huge amount of works, thousands of papers written on this subject. In the late 80s and early 90s. So those 2 examples just to show actually this philosophy works. I just show this philosophy works. Okay. But it's not possible if you want to go to higher dimensions. Yeah, actually there's one paper, let me just write it here. So there's one paper explains the philosophy. So here I did not give you many details. So how you write this G down, how you in principle can match with this thing. With another maybe 1 hour you can make this discussion a little bit more explicit, but I don't have time. But if you want, you can take a look at this paper. So this paper discusses the story for the matrix quantum mechanics. But in the section 2 of this paper, so this is a paper by Klebloff. So in the section of 2 of this paper, it explains this mapping of Feynman diagrams to the string action and this discretization picture. Give you a nice summary of that philosophy with more details than I have given to you. So you can take a look at that. And this paper also have some other references if you want to look at it. Okay. Any questions? Yes?
Historically, who was the first to realize this connection between the surfaces and topology of finite diagrams?
Sorry?
Who first realized this relation between topology and...
So already, of course, already went to Hooft. When he invented this Lagrangian expansion, he already noticed that this is similar to string theory. So he already commented on that. And but for many years, people did not make progress. People did not make progress. But in the late 80s, in the mid to late 80s, people start thinking about the question from this perspective, not from that perspective. So they start think about also from this perspective, because the string theory has, say, just typical string theory are hard to solve, etc. So people think maybe we can actually understand or generalize our understanding of string theory by discretize the worksheet, and by also discretize the worksheet, and then you just integrate over all possible triangulation, etc. And then they realize that thing actually is like summing over Feynman diagrams. And then for the very simple situations, say like say if you have only a matrix integral, that you can make the connection explicit. So that was in the late 80s. So people like McDowell or Kazakov, etc., they were trying to explore that. Other questions?
I'm having trouble seeing how the sum over all triangulations of these weak surfaces, how does that correspond to the discrete version of summing over all surfaces?
Right.
That's the discrete sum over all possible genus H, right?
Yeah. I think this is the example. Let's consider a torus. So a torus is a box with this identified with this and this identified with that. Okay. Yeah. Let me first just draw the simplest partition. Yeah, just draw like that. Let me just look at these two things. Say suppose I give each box. Say if I specify each box, give a unit area, give a unit, okay? And I do this one, I do that one, or I do some other ways to triangularize it, then corresponding to give a different metric to this surface. And then corresponding to integrate over all possible metric on this surface. And integrate over all possible metric on this surface, you can interpret as integrate all possible surfaces.
How about in the case of the strings, for example, we would sum over the torus here and the torus there and the torus there?
No, you're only summing over single torus. No, what do you mean by summing over torus here, torus there?
I thought like in the path integral, in the case of the string theory, for example.
No, you're only summing over a single torus. You're only summing over a single surface, but all possible ways to draw the surface. So what you said about the summing torus here, summing torus there, the corresponding what we call the disconnected amplitudes. And then you don't need to consider them in physically disconnected amplitude, you can just differentiate what we call by connected amplitude. And you don't need to do that separately. So once you know how to do a single one, and then disconnected one just automatically obtained by explanation.
Well, if the two configurations are homologous, they are sort of the same thing. And we just count in one. We are the side of this thing doesn't matter.
Sorry? No. Here we are only here the metric is matters. The geometry matters. It's not just topology.
But then the Feynman diagram care about this geometry.
Yeah. Just the key is that the propagator of the Feynman diagram essentially encodes those geometries, and of course encoded in a very indirect way. Yeah. read this part. This section only have a few pages, but contain a little bit more details than what I have here. Requires maybe 1 more hour to explain this in more detail. And which, yeah, this is just said. I just want to explain this philosophy. I don't want to go through the details on how you do this. Okay, good. So now let me just mention a couple of generalizations. So mention a couple of generalizations. So the first thing you already asked before, I think maybe both you have asked. Let me just mention them quickly. And if you are interested, I can certainly give you reference for you to read about them, or you can do it or I can put it in your T-set. And so far, it's all matrix valued field. Okay. But if you consider a theory like, or in other words, in the mathematical language, say it's in the joint representation. It's in the joint representation of the, say, because our symmetry is a UN, it's a UN gauge group. Okay? UN gauge group. But you can also, for example, in QCD, you also have quarks. So you also have field in the fundamental representations. So can also include, say, field in the fundamental representation. So rather than matrix valued, they are n vector. Okay, they are n vectors. So for quarks, of course, for the standard QCD, n will be 3. So you have 3 quarks. You have 3 different colored quarks. And so then in your Feynman diagrams, in addition to have those matrix lines, which you have a double line, and now here you only have a single index, okay? And then you only have a single line. So the propagator of those quarks, you just have a single line. And then also in your Feynman diagram, you can have loops of the quarks, etc. So you can again work this out, and then you find there's a very nice Lagrangian expansion. Very nice Lagrangian expansion. And then you find the surface, the diagrams, the Feynman diagrams. Now you find in this case, the Feynman diagrams can be classified by 2D surfaces with boundaries. Okay. So essentially, you have, for example, and let me just say, for example, this is a vacuum diagram for all the vacuum process. Okay, then you can say all the vacuum diagrams, and then they can all be classified. So previously, when you have a matrix valued field, then all your vacuum diagrams, they are corresponding closed surfaces, say sphere, torus, etc. But now if you include the quarks, then those surfaces can have boundaries and corresponding to the quark loops, etc. And
يمكن أن تلاحظوا سيطرة الفضاء ثنائي الأبعاد غير متناظر في هذا الأمر. يعني الآن الفيزياء تتحول بمخططات فايمان والسترينج وورشيت سترينج اللي هي دالة في سيجما وتاو. الآن ننظر إلى الفضاء ثنائي الأبعاد. يعني ربما تكون هذه فزلكة رياضية، لكن في النهاية في الفضاء ثنائي الأبعاد يكون الأمر أكثر سهولة في هذا الشأن. وهذا يعني أن سيطرة الفضاء ثنائي الأبعاد بالنسبة لصغر الأبعاد عند ثقل الأبعاد فالسيطرة تكون لفضاء ثنائي الأبعاد، وبالتالي المتغيرات تكون أقل. ولهذا يمكن أن نقول أن الفضاء ثنائي الأبعاد غير متناظر هي عبارة عن يعني في تحت الجروب ثيوري نظرية الزمر أنه نقول أنه 1,1 يعني 1,1 بالرغم من أنني يعني لم أطلع كثيرا على نظرية الزمر لكن أو نظرية المجموعات، لكن أقول أن 1,1 يمكن أن يخرج لنا 3,1 فضاء فيزياء لورنز أيضا يمكن أن يخرج لنا SU2 SU3 U1 كل ذلك يمكن أن يخرج لنا من 1,1. هذا ما أقوله أنا وهذا ما أعتقده، ولكن سيكون لنا إن شاء الله بإذن الله تعالى لقاء مع نظرية الجروب لن نناقشها كلها، ولما سنناقش فقط هذا الافتراض اللي هو 1,1 ربما سيكون يعني ما زعمت به يكون صحيحا. طيب تعالوا نواصل.
And then they cannot be classified. And so this also have a counterpart. If you try to map to the string theory, so this corresponding to string theory. A string theory with both closed and open strings. And so essentially those boundaries give rise to the open strings. So here it's all closed string, it's all closed surface. But now you can, by adding the open string, and then you can again have the correspondence between the two. Okay. So all the discussion is very similar to what we discussed before. We just apply all this same philosophy to the clocks. Yes.
Do the same trick on string theory and find some sort of expansion which then will map to some higher order surfaces, S3, 3 torus, 3 spheres.
Sorry, say it again.
I mean, from lines in Feynman diagrams we move to string theory to surfaces.
Yeah.
If there's some sort of expansion from surfaces, just they go one more step up.
You mean higher dimensions, not strings? Yeah, that will become, of course, that's a lateral idea. So that would be corresponding to, say, you can consider rather strings, you can consider two-dimensional surface. A two-dimensional surface moving in space-time. And then that would corresponding to so-called the membrane theory. But that theory will turns out string is a nice balance. It's not too complicated or not too simple, and give you a lot of structure. But when you go to membrane, then the story becomes too complicated, and nobody knows how to, say, quantize that theory. Yeah. So the second remark is that here we consider UN. So here our symmetry group is UN. Because our field, because of phi there is Hermitian. So when you have a Hermitian matrix, then there's a difference between the two indices. So we put one up and one down. So they are propagators. Then these two say these two lines with arrows because we need to distinguish up and lower indices. Okay, distinguishing two indices. But you can also consider, for example, phi is a symmetric matrix. So it's a real symmetric matrix. say real symmetric or real antisymmetric. In those cases, then there's no difference between the two indices. And then when you draw a propagator, so in this case, the gauge group, the symmetry group, would be say SON, say or SPN, etc. SPN, etc. And the propagators, they will no longer have orientations. Okay, they will no longer have orientations. Yeah, because you can no longer. Yeah, so this will give rise. Yeah, so let me write it closer. So this will give rise to unorientable surfaces. Okay, will give rise to, say, for example, to classify the diagrams, you can no longer just use orientable surfaces. You also have to include the non-orientable surfaces to classify the diagrams. And it turns out this also have a precise counterpart into unorientable strings. Non-orientable strings. Actually, I think non-orientable. Non-orientable surfaces. Also non-orientable strings. Okay. Good. So after emphasizing how difficult it is, if we want to start with say QCD, and then try to find its string theory description, but let's still nevertheless try. At least try. Yeah, for okay. So let's just consider. So let's consider just so just take notch n generalization say of QCD. So this again would be some UN gauge theory, UN Yamil theory, say in 3+1 dimensional Minkowski space, Minkowski space-time. And can we say anything about this string theory description? Okay. So nevertheless, so maybe it's difficult, but let's try to guess it. Okay. So in physics, in many situations, a seemingly difficult problem, if you know how to guess it, actually you can get the answer. Like, for example, quantum Hall effect, a fractional quantum Hall effect. You can just guess the wave function. So, of course, the simplest guess. So this is some gauge theory in 3+1 dimensional Minkowski space-time. So now we say this is a string theory. So natural guess is that this maybe is a string theory. Again, in the 3+1 dimensional Minkowski space-time. Okay. So we just take what So this would correspond to a stream propagating in, say, in this space-time, okay? So as I said, when you write down a string theory, you first have to specify your target space, which the string moves. The larger question would be just, should be the gauge series in Minkowski space-time, maybe the string theory should be, okay? And then you can just try to then you can just write down the simplest action. So maybe say number go-to action, which we wrote last time, okay? Or some or the say all Polyakov action. So this number of go-to action which we wrote the Polyakov. Yeah. Let me not worry about that. Yeah. For example, you can just guess. Say maybe this is a string theory. Also in the Minkowski space-time. Say consider the simplest action. This all the equivalent of this. Okay. Then at least what you could try. Now you have action. Now essentially have this object. Now essentially can compare. Okay. Now you can essentially compare. Say in QCD you calculate your Feynman diagrams and now just compare. But of course you still have the difficulty. Of course you have to go to strong coupling to see the geometric limit, etc. But in principle it's something you can do. But this actually does not work. Okay. This does not work. For the following simple reason. First, it has such a string theory. Say a string. So a string theory actually, the remarkable thing about the string is that if you have a particle, you can put the particle in any space-time. But strings are very picky. You cannot put them in any space-time. And they can only propagate consistently, quantum mechanically consistently, in some space-time, but not in others. So for example, if you want to put a string to propagate in this 3+1 dimensional Minkowski space-time, then you actually find that the theory is mathematically inconsistent. So such a string theory is inconsistent. It's mathematically inconsistent, except for say d equal to 26 or 10. Okay, so 26 is you don't, just purely have this theory, and 10 say if you also add some fermions.
طيب هنا ما الذي يميز هذه الأبعاد؟ لماذا السترينج تنتشر بروباجيت يعني في فضاء مناسب لها هي 26 أو 10؟ نحن نلاحظ شيء في هذه الأبعاد العالية، كلما زادت الأبعاد كلما قلت الكتلة. يعني توزيع الكتلة مع زيادة الأبعاد يؤدي لتقليل الكتلة، وهذا ما يعتبر ميزة إضافية للفضاء ثنائي الأبعاد للدفاع النفسي، أنه يقلل الكتلة بإضافة أبعاد إضافية. طبعا في الواقع نحن لا نرى أكثر من 4 أبعاد، وربما يكون هذه أقصى استطاعة يقدمها الفضاء ثنائي الأبعاد من أجل تقليل الكتلة. لكن الفضاء رباعي الأبعاد يعطينا حركة أكبر للكتلة، يعني مثلا السبين التوسع، يعني من آليات الفضاء ثنائي الأبعاد الدفاع النفسي هو التوسع والسبين والطرد الكتل الأعلى وموجات الجاذبية. كل هذه الأشياء لا يمكن أن تنتقل في بعدين، لابد أن تنتقل في 4 أو تعبر عن نفسها في 4 أبعاد. يعني السبين يجب أن يكون هناك 4 أبعاد. كتلة تلتف حول نفسها. هذه الكتلة تتوسع بجنب بالمنتصف وتنضغط بالأطراف حتى تكون السنجلاريتي عبارة عن دائرة، كما في معادلة ري كير أنه مركز الثقب الأسود عند الإسبين لن يكون عبارة عن سنجلاريتي، وإنما سيكون عبارة عن دائرة أو حلقة. وهذا بسبب ماذا؟ بسبب الأبعاد الرباعية، لكن في أبعاد ثنائية لا يستطيع أن. فبالتالي يعني هذه الجزئية أن نظرية السترينج تعبر عن نفسها في أبعاد أعلى، لأن السترينج كتلتها صغيرة كما سنرى، كتلتها صغيرة، وهذه الكتلة الصغيرة هي عبارة عن كتلة ضخمة، حتى لأن الفيزياء تتعامل معها بالفيزياء الكلاسيكية. تتذكرون ماذا قال المحاضر، ماذا قلنا عن الفيزياء الكلاسيكية؟ إننا يمكن أن نعتبر الهورز هذه والانتراكشن نستخدم سيمي كلاسيكال فيزيكس. طيب إذا استخدمنا السيمي كلاسيكال فيزيكس هذه يعني الكتلة ليست صغيرة، كتلة عالية، لكن من أجل أن نوازن بين الكتلة العالية هذه وميكانيكا الكم لابد أن نفترض أبعاد إضافية 26 أو 10 أبعاد، 10 أبعاد كافية. هذه الأبعاد الإضافية هي التي تقسم الكتلة. في نظرية لا تحتاج هذا الأمر، لأنه ما يقسم الكتلة ماذا؟ هو الفضاء وآلياته. يعني ناهيك من آليات الفضاء يمكن أن نعتبر كلما زادت الفضاء ثنائي الأبعاد، عدم التناظر في الفضاء ثنائي الأبعاد، كلما نقصت الكتلة، وبالتالي هذا الفضاء لن يحتاج، يعني نقاشنا نحن فيه لن يحتاج إلى أبعاد إضافية، فقط نتحدث عن الكتلة وكأن الفضاء ثنائي الأبعاد يعبر عن نفسه بكل أريحية، وبالتالي نعتبر الكتلة صغيرة. وهذا ما جعل نظريتي يعني بأبعادها الثنائية تتفق تماما مع نظرية الأوتار التي هي أبعادها 10 أو 11 كما سنرى لاحقا. يعني فنحن نتكلم عن ثنائي الأبعاد تتفق تماما مع أبعاد 10 أو 11 أو حتى 26. طيب تعالوا نواصل.
So such a string theory does not exist mathematically. So you say, oh, okay. You say, I'm a smart fellow. I can go around this. Because we want the Minkowski space-time, because those gauge theory propagating the Minkowski space-time, so this Minkowski space there must be somewhere. They cannot go away because all these group balls they live in this 3+1 dimensional Minkowski space-time. And if we want to identify the strings with those group balls, those strings must at least know some of this Minkowski space-time. And then you say, suppose you tell me that this string series only consists in 10 dimensions. But then let me take a string theory in 10 dimensions. Which is self-consistent. But I take this 10-dimensional space-time to have the form of a 3+1 dimensional Minkowski time and times some compact manifold. Okay. Some compact manifold. And in such case, so if this is a compact manifold, then the symmetry of this space-time, say the space-time symmetry, still only have the 3+1 dimensional, say, Poincare symmetry. Then, yeah, because if you want to describe the QCD in 3+1 dimension, QCD has the Poincare symmetry. You can do Lorentz transformation, and then you can do rotation, or you can do translation. The string series should not have more symmetries or less symmetries than QCD. They should have the same symmetry because they're supposed to be the same description. But if you take the 10-dimensional flat space, a 10-dimensional Minkowski space, of course, is not right because the 10-dimensional Minkowski space have 10-dimensional translation and 10-dimensional Lorentz symmetry. But what you can do is that you take this 10-dimensional space to be a form of the 3+1 dimensional Minkowski space-time and times some additional compact manifold. and then you have solved the symmetry problem. But except this still does not work, because the string theory, as we know, always contain gravity. And if you put the string theory on such a compact space n, that will always lead to a massless spin 2 particle in this 3 plus 1 dimensional part. But from Weinberg-Witten theorem we talked in the first lecture, in the QCD you are not supposed to have a 3 plus 1 dimensional massless spin 2 particle. Okay? And so this won't work. Okay, so this won't work. Because this contains in 3 plus 1 dimensional space, which is not present. Okay? Or in a larger version of QCD. So this does not work. So what to do? Yes?
So does this just mean like that it's mathematically inconsistent?
No, this does not mean it's mathematically consistent. It just means this string theory cannot corresponding to the string theory described QCD. The string theory description, the equivalent string theory for QCD cannot have this feature. Yeah, just say this cannot be the right answer for that string theory. This string theory is consistent. Yes? Yeah, that's right. Yeah, then this cannot be a description of that. From Weinberg-Witten theorem, we know in QCD there's no massless spin 2 particle. Yes?
I thought we have talked about maybe we can put spins point or just in a different package.
Yeah, we will go into that. But now they're in the same dimension because this Minkowski 4, this will have the gravity. This will have a. This will have a. Because this is the compact part, that doesn't matter. So in this part there is a spin, massless spin 2 particle. This is not present in QCD. So what can you do? So most people just give up. Most people give up. So option, so other than give up, the option is, say maybe this action is too simple. Maybe you have to look at a more exotic action. Okay, so this is one possibility. And the second possibility is that maybe you need to look for some other target space. Okay. But now, once you go away from here, everything else is like now becoming, say, search needle in the ocean, because then you don't have much clue to do. We just say your basic guess just cannot work. So for many years, even though this is a very intriguing idea, so people could not make progress. But now we have hindsight. So we know that even this maybe cannot be described by a 4-dimensional. Yeah, so if this, so even though this cannot have a, say, so this cannot have a, say, massless spin 2 particle in this 3 plus 1 dimensional Minkowski space-time, maybe you can still have some kind of graviton in some kind of a 5-dimensional space-time. Okay, you have some 5-dimensional in a different dimension. So there was some rough hint. Maybe you can consider it as a 5-dimensional string theory. But so let me emphasize, when I say 5 or 4, I always mention the non-compact part. So the compact part it doesn't count, because compact part just goes for the right. What determines the properties, say, of massless particle, etc., is the uncompact of the space-time. So yeah, because this is a 10-dimensional space-time, this is already not the. So maybe we change for change for string theory. In 5-dimensional, uncompact. Yeah, in 4+1, uncompact space-time. Okay. Yes.
When you say compact, do you mean mathematical definition of compactness?
Sorry?
When you say compact, do you mean the mathematical definition of compactness?
Yeah, that's right. Yeah, I just say say with a finite volume. Just for our purpose here, we can do it simply. Just let's imagine have compact always have a finite volume, for example. Yes.
Why can't we just ignore the compact dimensions? Is there any condition on how big they're allowed to be or something? Limit?
Yeah. Just when you have so if you know a little bit about this thing called the Closed-Klein theory, and you know that the compact part, the thing is that if you have a theory with uncompact and the compact part, and then most of the physical properties is controlled by the physics of uncompact parts, and this will determine some details like the detailed spectrum, etc. But the kind of thing we worry about whether you have this matter spin 2 particle, etc. will not be determined by this kind of thing.
Is there any volume limit on the compact part, maximum?
No, as far as I have a finite volume.
Just finite, but it can be large.
No matter how large, this have infinite. It's always much smaller than this one. Yeah, but large is always relative. It's always relative. Yes.
Tracking back though, is there any quick explanation for why 26 and 10 are special, or is it very
No, it's not complicated. Actually, we were going to do it in the next lecture. Yeah, next lecture we will see 26, but maybe not 10. Yeah, 10 is a little bit more complicated. Yeah, most people voted for my option 1, so that means you will be able to see the 26.
Wait.
Right.
Those numbers 26 and 10, they're specific to this Lambo direction, right? So for other direction would be something else.
It's specific for the Lambo, actually, the specific for the Lambo action is 26. And for the 10, you need to add some additional fermions and make it into a so-called superstring, then become 10. And this even this 26 one is not completely self-consistent. And anyway, there's still some a little bit tiny problem with it. Anyway, so normally we use 10. Okay, so now then there's some tantalizing hints for the, say maybe you cannot do it for the with a 3+1 dimensional uncompact space-time. Maybe you can do a 4+1 dimensional uncompact. So the first is the holographic principle. We have length. Holographic principle, we have length, because there we say if we want to describe a theory with gravity, then this gravity should be able to be described by something on its boundary. And the string theory is a theory with gravity. So if the string theory should be equivalent to some kind of QCD, some kind of gauge theory without gravity, and then from holographic principle, this field theory maybe should be one lower dimension. Okay? one lower dimension. Is the logic here clear? Say, so here we want to equate not J and QCD with some string theory. But string theory we know contain gravity. At least from all our experience contain gravity. And, but if you believe that the gravity should satisfy holographic principle, then the gravity should be equivalent, according to holographic principle, gravity in, say, in d-dimensional space-time can be described by something on its boundary, something one-dimensional lower.
So, but I thought the holographic principle was a statement about entropy.
No, it's a state started from a statement about entropy, but then you do a little bit of leap. So what I call a little bit a conceptual leap is that or a little bit leap of faith is that you promote that into the statement is that the number of degrees of freedom you needed to describe the whole system. Yeah, so the holographic principle is that for any region, if in the quantum gravity theory, for any region, you should be able to describe it by the degrees of freedom living on the boundary of that region. And the degrees of freedom living on the boundary of that region, then it's one-dimensional lower.
Wait, so can I ask one question about that? Like if I have some region, some volume in space, some like closed ball or something, and I live in a universe which is, for example, a closed universe, like maybe I live on some hypersphere or something like this, then how do I know whether how do I know that the information is encoded? How do I know whether I'm inside the sphere or outside of the sphere? Like, for example, we say that the entropy that has to do with the sphere basically tells you about how much information can be contained inside the sphere.
Yeah.
But if you live in a universe which is like closed or something, then you don't know whether you're inside or outside the sphere.
Yeah, but that's a difficult question. Yeah, if you talk about closed universe here, we are not talking about closed universe.
I see.
Yeah. Yes.
I thought the holographic principle is that the number of degrees of freedom inside the region is actually bounded by the area of the...
Right, it's bounded by...
Yeah, but why is it the degree of freedom, we use the degree of freedom living on the boundary?
Yeah, there are several formulations of that. First is that the total number of degrees of freedom in this region is bounded by the area. And then you can go to the next step, is that maybe the whole region can be just described by the degrees of freedom living on the boundary of that region.
Is that because say the state density on the boundary is like the state on the boundary is proportional to the area of the boundary?
Yeah, exactly. That's right.
So here our goal is to recover the Largent theory in 3+1 dimensions without gravity. So we have no gravity in 3+1.
That's right. Yeah, so if that is supposed to be equivalent to the gravity theory, and the gravity satisfies the holographic principle, and then...
طبعا المحاضر هنا ذكر معلومة في غاية الأهمية، إنه الهولوغرافيك طبعا اعتبر إنه n ناقص واحد أو dimensions دي ناقص واحد بالنسبة للفضاء السترينج، لأن الفضاء السترينج يحتوي الجاذبية. لكن هو ذكر شيء غريب، قال إنه degrees of freedom تكون مؤثرة في الباوندريز أوف الهولوغرافي أو في البلك بالنسبة لي. يعني عندما تقلل الأبعاد فإن degrees of freedom تعبر عن نفسها. وهذا ما سنراه لاحقا طبعا عندما يتحدث المحاضرة عن نظرية الهولوغرافي. ستكون ظاهرة جدا جدا أن degrees of freedom تعبر عن نفسها في السطح أو في الحدود، أقصى الحدود بالنسبة للبلك. البلك يعتبر إنه higher dimension والسطح يعتبر lower dimensions. النظرية دي تقول لا، طبعا النظرية لا تعتمد على الدايمنشنز أبدا. يعني الدايمنشنز اللي هو خروج الفضاء رباعي الأبعاد من الفضاء ثنائي الأبعاد، هذا أنا افترضته افتراض من طريق الواقع، افترضته افتراض وبالتالي قلت أنه الفضاء رباعي الأبعاد خرج. لكن ما يحدث كالآتي، أنه الفضاء ثنائي الأبعاد يتقارب حدوده الأبعاد تتقارب بفعل الكتلة. فعل الكتلة تعمل على أنه الأبعاد تتقارب من بعضها البعض. طيب تعالوا نشوف الفضاء ثنائي الأبعاد كيف هي أبعاده. هذه هي معادلة الفضاء ثنائي الأبعاد. هذه هي معادلة الفضاء ثنائي الأبعاد. في الحقيقة أنا هذا الفضاء أخذته من كوروسكل أو من إدينغتون على ما أظن، إدينغتون أو كوروسكل وشيكرز على ما أظن، أحد المعادلات يعني لا أستحضر تحديدا، لكن هذه المعادلات هي معادلات الفضاء ثنائي الأبعاد. هذه نجد أن الكتلة تعمل على تقارب الفضاء، تعمل على تقارب الفضاء مع بعضهم البعض، يعني يصبح يو قريب من في، يصغر يو ويتضخم في في ويصبح قريبان من بعض. طبعا هذا الفضاء، هذه المعادلات بصيغتها الحالية ربما تعبر عن شيء مختلف، لكن في النهاية إذا استخدمت نظرية معادلة الطاقة نجد الأمر واضح جدا. طبعا مع زيادة ام التي تزيد، مع زيادة ام التي اللي هو الزمن يزيد، وبالتالي نجد أن ربما الزمن يزيد أكبر من الام، وبالتالي نجد أن الكوش والسنج تتقارب مع بعضها البعض. وأيضا نجد أن في الحد الذي أمام الكوش والسنج نجد أن أيضا تتقارب الحدود مع بعضها البعض، وبالتالي يجعل دي يجعل يو قريبة من في. هذا ما يتعامل به فضاء ثنائي الأبعاد مع الكتلة. لكن خروج البعدين الآخرين هذه أضفته أنا من عندي، لأنه الواقع يقول ذلك، أنه هناك أربع أبعاد. وبالتالي طيب نرجع للفيديو مرة أخرى حتى نشوف أين وقفنا نحن. وبالتالي نجد أن نجد أن أنا معادلتي ما دام لا تعتمد على عدد الأبعاد، تعتمد على شيء واحد، وهذا ما يجعلها شاملة وتتفق تماما. في خصوص ما يتفق ما يقال أن البلك degrees of freedom تكون فيه قليلة، وأن الباوندريز degrees of freedom تكون عالية وتعبر عن نفسها بأفضل. في نظرية تقول كالآتي: داخل الثقب الأسود فإن الفضاء السلايسز أو المدارات في الفضاء تزيد أبعادها كلما اتجهنا من ناحية المركز. ونحن نعرف من آليات الفضاء أو من خصائص الفضاء ثنائي الأبعاد أنه يخفي القوى الأساسية الثلاث، وبالتالي كلما زادت السلايسز أو زاد التباعد بين المدارات تم تخفيض القوى أو قمع القوى الأساس الثلاثة. يعني نحن من خلال بعدين فقط استطعنا أن نعبر ما سيقوله المحاضر في خلال 4 أبعاد أو في خلال 10 أبعاد فقط بعدين. عدم التناظر في الفضاء ثنائي الأبعاد أو عدم التناظر ما نقصد به أن يو أكبر من في. عدم التناظر هو السبب في الأساس في أن القوى الأساسية الثلاث لا تعبر عن نفسها، وبالتالي الديجريز في فريدم لا تعبر عن نفسها، الفلكشويشنز لا تعبر عن نفسها، الويف فانكشن دالة الموجة لا تستطيع أن تعبر عن نفسها، وهكذا الكتلة لا تستطيع أن تعبر عن نفسها. الحركة تعيق الحركة يعني السرعة لا تكون عالية، كما ناقشنا ذلك في فويجر 1 وفويجر 2، الفيديو الخاص بفويجر 1 وفويجر 2 ذكرنا أن الفويجر 1 وفويجر 2 مفترض أن تتباطأ الآن لأن هي بعيدة جدا عن الشمس والفضاء ما بين النجوم. هذا الفضاء يتحول إلى فضاء ثنائي الأبعاد، وبالتالي يعيق الحركة بالنسبة للجسيمات أو الأجسام التي تكون بداخله، عكس الأجسام التي تكون بالخارج من هذا الفضاء فإنها يراها أنها تسير بنفس السرعة، لكن في الحقيقة هي حركتها تعاق. جميل. فنظرية من خلال الفضاء ثنائي الأبعاد تستطيع أن تعبر عن هذا الشرط الذي ذكره المحاضر بكل أريحية دون ما أن نفترض أبعاد إضافية دون ما أن نفترض أن نقول أننا نستخدم فزلكات رياضية بحيث أننا نفترض أبعاد إضافية حتى تكون الرياضيات كونسيستنت وكذا، لكن نظرية لا تحتاج لكل هذا. الأمر بسيط جدا. طيب تعالوا نواصل.
The natural gas is that this non-gravitational field theory should live in one-dimensional lower. Okay, so this is one hint. And the second is actually from the consistency of string theory itself. Okay. So this is a little bit technical. Again, we will only be able to explain it a little bit later when we talk about more details about string theory. It turned out even though the string theory in this space is inconsistent, but there's a simple way. It's not a simple way. Yeah, so what's happening is the following. So if you consider, say, a string propagating in this space-time, and there's some symmetries on the worksheet. And only in the 10 and 26 dimension, those symmetries are satisfied quantum mechanically. And in other dimensions, those symmetries somehow, even though it's classically it's there, but quantum mechanically it's gone. And those symmetries become, because they're gone quantum mechanically, then they lead to inconsistencies. And turns out, they lead to inconsistency. It turns out that there's some other way you can make that consistent, to make that symmetry still to be valid, is by adding some new degrees freedom. Okay, there's some new degrees freedom dynamically generated. And that new degrees freedom turned out to behave like additional dimension. Okay, this will make no sense to you. I'm just saying you a consistency of string theory actually sometimes can give you one additional dimension.
What is the difference between these inconsistencies you're talking about and like anomalies?
Yeah, it is anomalies. Okay. Yeah, but here it's called gauge anomalies. Okay. Yeah, it's gauge anomalies. It's at the local symmetry anomalies, which is inconsistent.
So just maybe this is not the time to ask it, but are the degrees of freedom that you need to like save you from this inconsistency problem? So they could, if they look like, do they have to be extra dimensions of space, or what I'm saying is that if we need to do string theory in 10 dimensions, is it really 4 dimensions plus 6 degrees of freedom, or are they actually 6 quantified spatial dimensions?
No, this is a very good question. Say if you have, say, this is something we will be a little bit more clear. Just even oh, it's very late. Even second part of this lecture, is that here you have 6 degrees 4 degrees freedom. You have 6 degrees freedom. Yeah. But turns out, if you only consider this guy, then this 4 degrees freedom by itself is not consistent. Say there's some violation of the symmetry at the quantum level, and then you need to add more, and then one more, then corresponding to have extra dimension. Yeah. Anyway, we can make it more explicit in next lecture. Yeah. Here I just throw a remark here. Anyway, this guy, this is purely hindsight. Nobody have realized this point, this first point. Nobody have realized it before this holographic duality was discovered. Okay, nobody really made this connection. Nobody made this. And this point, from this point, saying there should be a 5-dimensional string theory describing spin 2 particle, describing a gauge theory, that was made just before the discovery. I will mention that a little bit later. Anyway, so now let's, let me just maybe finish this, then we have a break. So now let's consider, suppose there's a 5-dimensional space-time string theory in some 5-dimensional space-time, say 4 plus 1 dimensional space-time, say describe QCD. then what should be the property of this y? Okay, so this y denotes this some manifold y. Okay, so as I mentioned, it must have at least all the symmetries of the QCD, but not more. Should have exact the same amount of symmetries. So that means you must have the translation and the range symmetries of QCD. Okay? So that means the only metric I can write down must be of this form. The only metric I can write down, the metric must have this form. So this AZ is just some function, and Z is the extra dimension to a Minkowski space-time, and this is a Minkowski metric for 3+1 dimension.
You mean it's like to 4 dimension? We have to get the Minkowski space.
Yeah, I just say whatever this space, whatever is the symmetry of this space. So the symmetry of this space-time must have the Poincare, must have all the symmetry of the 3+1 dimensional Minkowski space-time. Then the simplest way, essentially the only way to do it is just you put the Minkowski space-time there as a subspace. And then you have one additional space, and then you have one additional dimension. And then because you have to maintain the symmetry, then with a little bit thinking, then you can convince yourself the only degree of freedom, the only additional degree of freedom in the metric you can allow is an overall function, say the function of this z, and nothing else.
طبعا ربما لاحظتم هذه المعادلة شبيهة بمعادلة فريدمان، أو لها نفس التركيبة ولها بعض الخصائص الشبيهة بفريدمان. يعني مثلا الحد الأول اللي هو السكيلين فاكتور، هو شبيه بالسكيلين فاكتور لمعادلة فريدمان. وبعدين عندنا معادلة مينكوسكي، وعندنا الحد الأول قبل معادلة مينكوسكي اللي هو دي زد سكوير، هذا اكسترا دايمنشن. وبعدين معادلة مينكوسكي، وبعدين الحد الأول الحد A تربيع نعم اوف زد، هذا يعتبر السكيلين فاكتور وهو سبب التوسع. يعني هذه المعادلة قريبة من معادلة مينكوسكي، معادلة فريدمان. وهذا يدل على ماذا؟ هذا يدل على انه السكيلين فاكتور يمكن يعتبر واحد في كل الأحوال. طبعا ربما تستغربون من هذا الأمر، لكن تعالوا أخبركم بشيء غريب في نظرية على يوسف يؤكد على هذا الخبر. معادلات الطاقة والزمن. معادلات الطاقة، المعادلة الأولى معادلة الطاقة، والمعادلة الثانية معادلة الزمن. وانظر إلى يو ناقص في، بعدان للفضاء ثنائي الأبعاد غير المتناظر، والزمن يعتبر إمرجنس، والطاقة تعبر عن معادلة الفضاء. عندما نطرح فيو ناقص في تعطينا الطاقة عندما نضربها في جاما أس ناقص واحد، وهي تسمى بكمية التحرك. تؤثر فيه الجاذبية تأثير قوي جدا. المهم ما أريد أن أقوله أن هاتين المعادلتان أو هاتين المعادلتين هي معادلات متصلة من أبعاد بلانك وإلى أضخم الأبعاد. معادلات متصلة من أبعاد بلانك 10 أس ناقص 35 متر، و10 أس ناقص 42 ثانية إلى أضخم الأبعاد وما دون أبعاد بلانك حتى. وبما أن الفضاء ثنائي الأبعاد متصل تماما عند هذه الأبعاد فإنها، وبما أننا ناقشنا في سلسلة النسبية العامة الجزء الأول والثاني علم الكونيات صمود وثبات هذه المعادلات، فإن هذه المعادلات أيضا تكون متصلة عند الأبعاد الصغيرة، وهذا يعني أن ما يخرج منها يكون مشابه تماما لبعضه البعض، وهذا ما خرج منها هي معادلة فريدمان. إذا نتوقع أن عند السترينج ثيوري فإن المعادلات التي تخرج هي معادلة شبيهة لمعادلة فريدمان بشكل أو بآخر، لكنها شبيهة بمعادلة فريدمان من ناحية السكيلينج فاكتور ومن ناحية مينكوسكي سبيس. طبعا مينكوسكي سبيس لابد أن يكون موجودا، لأنه هذا السبيس الذي نراه نحن، يعني نحن نعيش في مينكوسكي سبيس، فأي شيء يجب أن نرجعه إلى مينكوسكي سبيس. فيمكنكم الرجوع إلى تلك السلسلة، سلسلة علم الكونيات، النسبية العامة وعلم الكونيات، مقارنة مع نظريات على يوسف، وله جزئين، الجزء الأول والجزء الثاني. طيب تعال نرجع.
Can that be also kind of a scalar in Minkowski space?
Yeah. Let me just say, this is most general matrix. It's 4-dimensional, 3 plus 1 dimensional. Contrast image.
Why this additional dimension always in the space part? Can it be in the time-like part, like 3 plus 2?
Both arguments suggest it's a space part. So because this is just the boundary of some region, that's a spatial dimension reduction, not a time. Yeah. So is this clear to you? Because you want to have a Minkowski space-time, so you must have a Minkowski here. And then in the prefactor of the Minkowski, you can multiply by anything, any function, but this function cannot depend on the x. It can only depend on this extra dimension. Because if you have anything which depends on capital X, then you have violated the Poincare symmetry. You have violated the Lorentz symmetry. You have violated the translation in the X. Then the only way, so the only function you can put before this Minkowski space-time is a function of this additional dimension. And then by redefining this additional dimension, I can always put this overall factor in the front. Yeah, so this tells you that this is the most general matrix. Okay? So if it's not clear to you, think about it a little bit afterwards. So this is most as you can do. So that's the end. So you say you cannot determine AZ, etc. So this is as most you can say for the QCD. Okay. But if the theory, if the field theory is scale invariant, say a conformal field theory that normally we call CFT, okay? Say a conformal field theory. Then we can show this metric. So let me call this equation 1. Then 1 must be anti-de Sitter spacetime. Yeah, I'm going to show that. So if the field theory is scale invariant, that means that the field theory have some additional symmetry should be satisfied by this metric. And then I will show that this additional scaling symmetry will make this to precisely a so-called anti-de Sitter spacetime. Okay? Yeah. Right. If the field theory, say the QCD does not have a scale. It's not scale invariant. I do not say QCD anymore. Just say suppose some other field theory which have a Lagrangian expansion, which is also scale invariant, and then there must be, then the corresponding string theory must be in under de Sitter space. Oh, that's it. No, we will come back to QCD, but the somewhat indirect way. Yeah, not to the not to your real life beloved QCD.
So no one solved that problem still?
Yeah, no one solved that problem. Yeah. Yeah, so you still have a chance. So the argument is very simple. So let me just say it, then we'll have a break. Then we will done. Yeah, I think I'm going very slow. Scale invariant theory is invariant under the scaling for any constant lambda. Okay. So scale invariant theory should be invariant under such a scaling. And then we also, now we want to require this metric also have some this scaling. It's okay. So now require 1 also have such scaling. Such scaling symmetry. Okay, so we just do a scaling x mu, go to lambda x mu. And then this term will give me additional lambda square. So we see in order for this to be the same as before, the z should scale the same. Okay? So in order for this to be, so we need these to scale as the same. In order I can scale this lambda out. After I scale this lambda out, I also need that a lambda z should be equal to 1 over lambda az. Okay? So the scaling symmetry of that equation requires these two conditions. So under scaling of z, this a lambda z should satisfy this condition. Okay? Then the lambda will cancel. So this condition is important because we need to scale them homogeneously, otherwise, of course, lambda will not drop out. And the second condition, just make sure lambda is cancelled. Okay, is it clear? So now, this condition then just determined that az must be a simple power. Must be written as r divided by z. R is some constant. Okay? And now we can write down the full metric. So now I've determined this function up to an overall constant. So the full metric is ds squared equal to r squared divided by z squared, z squared plus eta mu mu dx mu. And this is precisely a ds metric written in certain coordinates. And this r, then is just the curvature radius of a ds. So if you don't know about anti-de Sitter spacetime, it doesn't matter. So this is a metric, and the name of this metric is anti-de Sitter. And later we will.
طبعا هذه المعادلة في غاية الأهمية في هذه السلسلة، يعني في غاية الأهمية، وهي توضح طبعا نظرية على يوسف بدرجة أكبر. كيف ذلك؟ إذا صغرت زد طبعا هو بعد إضافي، إذا صغرت زد فإن دي اس ستكبر، وبالتالي سيختلف شرط مينكوفسكي. وإذا تضخم الزد فإن دي اس تنقص، وهنا أيضا يختلف شرط مينكوفسكي أو فضاء مينكوفسكي. فيمكن اعتبار أن فضاء مينكوفسكي يعتمد على زد. طبعا لا يختلف، يعني يكون هناك فضاء مينكوفسكي لكن تحت شروط قاسية، شروط معينة، وبالتالي فضاء مينكوفسكي يعتمد على زد. أيضا يعتمد على ار، وار هو كيرفيتشر، بالتالي ما يسمى بالجاذبية تلعب دورا كبيرا جدا في فضاء مينكوفسكي. وهذا ما توضحه نظريتي بطريقة أخرى، بحيث أن الفضاء من أفق الحدث وانت داخل يتقسم هذا الفضاء ويكبر هذا التقسيم وتداخل نحو المركز. وبالتالي ما يحصل هو أن يجب أن الجسيمات حتى ترى الفضاء حولها وفضاء مينكوفسكي يجب أن تتغير هي أيضا، أبعادها تتغير. وخارج أفق الحدث أيضا فإن الفضاء يتقسم، يزيد التقسيم، وبالتالي الجسيمات أيضا يحصل لها نفس الأمر. وهذا يعني أنه كلما زاد التقسيم أو زاد السبيسينج، مسافة بين التقسيم، فإن الجسيمات لابد لها أن تصغر، سواء كان داخل الفضاء أو خارج الفضاء. فضاء أفق الحدث بالنسبة للثقب الأسود، هذا طبعا ينطبق على فضاء داخل البروتون. في الفضاء داخل البروتون نجد أن الكوارك كتلتها صغيرة، ولكن 3 كواركات فقط هي كافية تماما على أنها تغطي البروتون ككل. وهذا أمر شبيه تماما بما ذكرته في قبل الآن، يعني في أنه الجسيمات لابد لها أن تصغر في الفضاء الداخلي. كلما تعمقنا داخل أفق الحدث، تعمقنا نحو الثقب الأسود، فإن الفضاء أن الجسيمات لابد أن تصغر، لكن طاقتها كبيرة في الجاذبية، طاقتها كبيرة. طبعا الثقب الأسود يختلف من البروتون، أن الثقب الأسود لديه مركزه أو حركة، اتجاه للحركة، حركته ناحية المركز، لكن البروتون ليس لديه اتجاه حركة نحو المركز. البروتون لديه كتلة يمكن أن نقول متجانسة، أو ليست كتلة، نقول طاقة متجانسة، لكن هذه الطاقة تزيد كلما تعمقنا تحت عميقا داخل البروتون أو النيوترون. وبالتالي نجد أن الكواركات الموجودة داخل النيوترون والبروتون تكون لها حركة ضخمة جدا بحيث أنها تغطي كل البروتون. 3 كواركات فقط، لو جمعت الطاقات وكتل هذه ال3 كواركات لن تفوت 10 ميجا. بالرغم من ذلك فإن طاقتها تغطي البروتون كله، والذي هو 1 جيجا. انظر الفرق، 10 ميجا قصاد 1 جيجا، يعني 1 من 100. هذه بالنسبة للكتلة، لكن الطاقة عالية، الطاقة عالية جدا، الطاقة عالية. فنجد هنا المؤثر في ذلك هو الكيرفيتشر وزد، كيرفيتشر ار سكوير وزد. يعني هذه المعادلة تعبر لنا عن هذا الأمر بطريقة أو بأخرى، بR تربيع على Z تربيع، هو الذي يعطينا فضاء مينكوفسكي في الفضاءات المختلفة للجاذبية. وهذا ما يجعل الفضاء الداخلي للبروتون هو شبيه تماما بالفضاء الداخلي للثقب الأسود. حتى الفضاء الداخلي للذرة، وحتى الفضاء مينكوفسكي الحالي الذي نجلس فيه نحن هو شبيه تماما بالفضاء الثقب الأسود. لكن حتى يكتمل الشبه يجب أن الجسيمات داخل الثقب الأسود تصغر كتلتها بحيث أنها لا تتأثر، يعني تصغر كتلتها تصغر بحيث أنها لا تتأثر بالجاذبية فقط، هذا ما يحصل. وأيضا الفضاء داخل البروتون أيضا لابد له يتغير، وأن كتلة الأجسام تصغر بحيث أنها لا تتأثر بطاقة البروتون، وهذا ما يجعل الفضاء ثنائي الأبعاد غير متناظر، والفرضيات التي خرجت منه صالحة في جميع الفضاءات. وهذا ما يجعل هذه المعادلة تتفق مع نظريتي، ويجعل هذه المعادلة يمكن وصف بها الإيكوفالنس بين فضاء أنتي ديسيتر وفضاء الكونفورمال كيو اف تي أو نعم كونفورمال هو الميكانيكا الكم في فضاء مينكوسكي. طيب تعالوا نواصل.
Later we will explain the properties of the anti-de-Sitter space-time. So now we reach a conclusion is that if I have a large M conformal field theory in Minkowski d-dimensional space-time, so this can be applied to any dimensional, so not necessarily 3 plus 1 in D. So this, if it can be described by a string theory, should be string theory in ADS D plus 1. Okay? And in particular, the 1 over n here is related to the G string here. Okay, the string coupling. So this is what we conclude.
طبعا نحن عرفنا جي، ولكن لا نعرف حتى الآن n وكيف تعبر نفسها. طبعا نعرف n أنها عبارة عن numbers of phases في تعديل توفت جيرارد توفت لفايمن دياجرام كما شرحناها في الفيديوهات السابقة، لكن هناك تعديلات وهناك تعبيرات أقوى لn سنراها في مقتبل الفيديوهات.
Yes. So all we showed is that there is no obvious inconsistency with that correspondence.
What do you mean there's no obvious?
As in, like, we didn't illustrate in any way that they...
Sure. I'm just saying this is a necessary condition.
Right. So at least that is necessary.
Yeah, this is a necessary condition. So if you can describe a large N CFT by a string theory, and it should be a string theory. Yeah. This proposal works. This proposal passed the minimal test.
So when Maldacena presumably actually did figure this out, you said that this resulted with the holographic principle, like it was just figured out right before he did it. Was he aware of the holographic?
No. Here is what I'm going to talk. So Maldacena, in 1997, Maldacena found precisely. In 1997, Maldacena found a few examples of this, precisely realized this. And not using this method, using some completely indirect way, which we will explain next. So he found this through some very indirect way. But in principle, one could have realized this if one kept those things in mind. So now let me tell you a little bit the history, and then we will have a break. Then we can go home. So it depends on whether you want a break or not. Maybe you don't want a break. Yeah, let me tell you a little bit history. So in just to save time, let me not write it down, just say it. So in late 60s to early 70s, so string theory was developed to understand strong interactions. Okay, so understanding strong interactions was the problem at the time. People were developing string theory, try to understand strong interactions. So in 1971, of our friend Frank Wilczek and other people, they discovered the symptotic freedom, and then established, say, the Yang-Mills theory as the description of strong interaction, which now have our QCD. And so that's essentially eliminated the hope of string theory to describe QCD. Okay? Because the QCD seems to be very different. Eliminated the hope of a string theory to describe strong interaction, because the QCD, SU3 gate theory, is very different from the string theory. So people soon abandoned the string theory. So now we go to 1974. So 1974, a big number of things were discovered in 1974. So 1974 was a golden year. So first is to hope to realize his Lagrangian expansion, and realize this is actually looks like a string theory. And then, completely independently, Shirk, Schwartz, and Yulia, they realized that string theory should be considered a theory as a gravity rather than a theory of strong interaction. So they realized actually, it's ironic, people started doing string theory in the 60s and 70s, etc. But only in 1974, people realized, string theory always have a gravity, and should be considered a theory of gravity. Anyway, so in 1974, they realized that string theory should be considered a theory as a gravity. So that was a very, very exciting realization. Yeah, because then you can have quantum gravity. But by that time, people have given up on string theory. So nobody cared about this important observation. Nobody cared about this important observation. So also in the same year, in 1974, Hawking discovered his Hawking radiation, and then established that black hole mechanics is just is really a thermodynamics. Then really established that black hole is a thermodynamic object. And in 1974, there's also another important discovery, which is related to MIT, so that's why I mention it, is that the people first really saw quark experimentally. Is that our friend, colleague Samuel Tin at the Brookhaven, which they discovered the so-called charmonium, which is the bound state of the charm quark and the anti-charm quark. And because the charm quark is very heavy, so they form like a hydrogen-like structure. So in some sense, the charmonium is the you first directly see the quarks. And actually, even after the 1971, after asymptotic freedom, many people did not believe QCD, did not believe quarks. They say, if there's a quark, why don't we see them? And then in 1974, Samuel Tin, they discovered this charmonium in October, and so people call it the October Revolution. Do you know why they laugh? Okay. Right. Yeah. Anyway, yeah. They call it October Revolution. Right. Yeah, because I saw your emotions, I think you have very good composure. Anyway, in the same year, in 1974, Wilson proposed what we now call the lattice QCD. So he put the QCD on the lattice, and then he invented, and then he developed a very beautiful technique to show from this putting QCD on the lattice that actually the quark can be confined through the strings. So the quarks in QCD can be confined through strings. And then that essentially revived the idea maybe the QCD can be a string theory because the quarks are confined through the strings. It's all happened in 1974. So then I mentioned, say, in the late 80s and early 90s, people were looking at these so-called matrix models, the matrix integrals, etc. Then they show they related to some lower dimensional string theory, but nobody. Yeah, they showed this related to some kind of lower dimensional string theory. And then in 1993 and 1994, then 't Hooft had this crazy idea of this holographic principle. He said maybe things about the quantum gravity can be described by the things living on the boundary. And it's a crazy idea. Very few people paid attention to it. But the only person who paid the only person who picked it up is Lenny Susskind, and then he tried to come up with some thought experiment to show that that idea is not so crazy. Not so crazy. So actually, Susskind wrote a very sexy name for his paper. It's called "The World as a Hologram," and yeah. Anyway, so that paper received some attention, but still people did not know what to make of it. And then in 1995, Polchinski discovered so-called deep brains, and discovered so-called deep brains. And then we go to 1997. So in 1997, first in June, so as I said, that QCD may be some kind of string theory. This idea is a long idea, starting from the Lagrange expansion, and also from the Wilson picture of confining strings from the lattice QCD, etc. But it's just very hard problem. From QCD, how can you come up with a string theory? Just very hard. Very few people were working on it. So in 1997, in June, Polyakov finally, he said, had a breakthrough. He said that this consistence of string theory give you one extra dimension. You should consider a 5-dimensional string theory rather than a 4-dimensional string theory. And then he gave up some arguments. Anyway, and he almost always actually write down this metric. Maybe he already wrote down this metric. I don't remember. Anyway, he was very close to that. But then in November, the Madasina came up with this idea CFT, and then he provided explicit examples of certain Nagier gauge series, which is scale invariant, and some string theory in certain antecedent space-time. And as I said, through the understanding of these D brains, But even Madasina's paper, he was still thinking from the picture of Nagier gauge theory corresponding to some string theory. He did not make the connection to the holographic principle. And but very soon, in February 1998, so Witten wrote the paper, and he made the connection. He said, this is precisely the holographic principle, and this example, then he said, this example is precisely the holographic principle Susskind and Totbot was talking about. Yeah. So that's a brief history of how people actually reached this point. So the next stage, what we are going to do is to try to derive this thing. So now we can have, as I said, we can have two options. We can just start from here. So assuming there is some CFT, it's equivalent to some string theory, and then we can see how we can develop this further. And this is the one option we can take. And another option is to really see how this relation actually arises from string theory. And many people voted for the second option, which in my email is option 1. So you want to see how this is actually deduced from string theory. So now we will do that. Okay? But I should warn you, there will be some technicality you have to tolerate in order to see how this is derived. Okay? So we do a lot of 20 minutes today without break? Good, okay. Yeah, next time I will remember to break.
تمام، فإن شاء الله سيكون هذا الديريفيشن سيكون في محاضرة قائمة بذاتها إن شاء الله، ونكتفي بهنا، والسلام عليكم ورحمة الله وبركاته.